screen for a while, right? I forgot to enable annotation. Okay, got it. Okay, here's a very quick revision of acid and base so that we can use it for salt preparation, right? To summarize it very briefly, acid only reacts with base only reacts with acid. Acid don't react with anything else, base don't react with anything else. I think that's the summary for O level. So anything that reacts with acid is base. Anything that reacts with base is acid. That is the reason why you learn to identify, oh, these things are acid. Oh, those things are base. So that when you see them together, oh, confirm they will react one. And they will react in a very predictable way, right? This is me testing whether you know all the list of acids from O-level syllabus. One more time. You are expected to immediately know when you see them. Oh, those are acids. You are expected to know, oh, these things are base. If you don't, to be fair, that is unnecessary suffering. They are not very difficult to memorize anyway. So this will be your first. Now, let's start with the acid list. The acid list is easier, probably. Okay, let's take turn, yeah. Aiden, give us one acid.
HCl.
And I will prefer this lah, the chemical formula, not the English name lah, so to speak. Yeah. Now Joshua.
H2SO4.
Next, Aiden.
HNO3.
Next, Joshua. Anything else that you may remember? Just put it in first, yeah. HTPO4, a bit rare, right? Anything else, Aiden? Aiden has gone through this, so Aiden will know, right? Aiden, if there's anything else that you know.
H2CO3.
Right, there you go. Boxing this guy. Pay attention to it later, yeah. Boxing this guy. Anything else, Aiden?
I know there's citric acid, but
yeah, citric acid, you don't know the chemical formula, but you will know ethanoic acid. In fact, both of them should know.
so ethanoic acid is CH3COOH.
Should sound familiar. I'm going to add a few more, which if I say should be obvious that they are acids. They're not very popular, but they are still acids. Right? They're still acids. For example. Right. All this, when you see them, usually you will know they're acids. They are the easier one to recognize, right? There isn't much other in O level that they ask you, right? One more class, which is very important, your acidic oxides. Let me confirm, Aiden, have you covered acidic oxides?
I think I heard of it somewhere in my class.
Right. Let me explain it, right? So acidic oxides is very easy to understand, but you don't usually think of them as acids. I'm giving this a very big emphasis. They are acids, right? Their name suggests acidic oxide means they have oxides. Oxides means oxygen with somebody else in front, usually, but not like SO4. SO4 is not oxide. Let me show what's an oxide. For example, CO2 is an oxide, low carbon dioxide. Even the name is oxide, carbon dioxide. Whether we know or not, CO2 is very slightly acidic, but it is acidic. Let me give you an example of acidic oxides. Another with O, so NNO2. Nitrogen dioxide. Nitrogen dioxide is acidic. Do we know that? I don't think so. It's a very weak acid anyway, right? But it is still acidic. How do we memorize it? It's very simple. Acidic oxides are always non-metal compared with oxygen. Simple, right? Okay, let me give you another oxide. Na2O. Joshua and Aiden, is this acidic oxide or not?
Yes.
Aiden, yes. Joshua?
Sodium oxide.
It is an oxide lah. That one we're sure lah. But is it acidic?
No, because it has a metal.
Right.
Uh,
So Aiden and Joshua, very easy to identify. Oh, this is metal, right? Sodium is metal. Therefore, well, simple. Life is simple. Turns out basic or alkaline, right? Basic. So this is called metal oxides, which is, well, you choose usually basic, usually basic. There you go. Okay.
Okay.
All oxides are now either acidic or basic at this point. We just don't think about them naturally that way, but they are. Most of them are very weak, but some of them will be very strong. Please, from now on, consider them as basic or acidic. Okay, that's very fundamental in the chapter. Any questions so far?
No.
Right. Okay. Now, for acidic oxides, I'll give you the exception. In the syllabus, they tell you, yo, non-metal oxide must be acidic with 3 exceptions. So instead of memorizing anything else, memorize the exceptions. The exceptions are H2O, to nobody's surprise. Water, which is dihydrogen oxide. Okay, never call it that, just call it water. But that is an oxide of hydrogen and it is neutral, right? So except this guy, except CO and except NO. Now this is to be memorized. Okay, this is the exception. Again, you memorize the exception, you should remember that, oh, therefore, not in exception, acidic oxide. Okay, any questions? Exception for metal oxide. Exceptions also exist for the metal oxide, which is supposed to be basic. So that NO, zinc oxide, okay, aluminium oxide, and lead oxide. They are amphoteric. It's a very fancy word for they can become acid or base depending on the situation. So one more time, zinc oxide is basic if he meets acid. Zinc oxide, strangely speaking, can become acid if he meets another base, right? So now let's see what's the implication here. Now, HCl meets Na2O. Will they react or not, Joshua?
Yes.
You may not know what they become, but they will react. That's the most important thing for now.
Yeah.
Okay. But what's the reason?
Acid and one is base.
Yep. That's it. Acid meets base, they react. Right. Okay. Now, let's say, I don't know, this guy meets this guy. He react or not?
It will not react.
It will in a very small amount, but it will still, because carbon dioxide is acidic and sodium oxide is acidic. However, this guy is very weak, but that's beside the point for now. This and this will react given the time, because one is acidic, very weak, and one is basic, rather strong. Okay. You, however, won't think of it that way. Fair. You, however, won't think of it, but given time, they will and do react. Now, will sodium oxide react when it meets zinc oxide? Joshua.
No. Oh, yes, sorry, yes.
Yes. Why is that so, however? Why?
Because zinc is Zinc oxide is a acid, right? It can be either.
It can be either. So if he meets a base, he will take the chance to become acidic.
Yeah.
However, the reaction is very difficult for us to predict, at least in O level. But just have a concept that they do react. They do react. Okay. Last one, Aiden, will CO react with ZNO?
CO, no, because CO it's like neutral.
Yep, it's neutral. So you won't have an acid-base reaction. At the very least, we'll say that. Not every reaction is acid and base, right? But at least acid and base reaction not gonna happen. Something like that. It doesn't mean that other form of reaction will not happen. But you know what? Today we just talk about acid and base. Yeah, just that. Okay. So at this point, you have all the list of the acids that you're supposed to recognize directly. This is really all. Okay. And basic one, I'll just spell it out to you. They're actually much easier, right? They're actually much easier, right? Metal hydroxide, metal oxide, and metal. There you go. That's the list for alkali or basic stuff. That's it. Look.
Oh.
Metals are basic, therefore will react with acid. Metal hydroxide are basic, therefore will react acid. Metal oxide, la. Yeah, that's it. That's it. Very all metal stuff lah. Everything metal lah. Okay. This is the minimum definition or minimum practical use lah of acid and base that you have to know in O-level syllabus. Very rarely your teacher may say something out of this, or sometimes the exam paper will take something from the A-level syllabus and expand upon this definition. We don't care right now. This is enough for you, and you do need to know this. This is the minimum definition. Any questions so far? Yeah. Now, I will now talk about two special guys. NH4OH and H2CO3. These are the two special. One in each chem, one acid and one basic. They are both weak. Weak acid means you don't get. Never mind. I'm not going to explain that for now. They are both weak acid and weak bases. However, there's one more thing that I need to discuss with you. They are both shy. I have to explain this very clearly what it means. Now, in O-level syllabus, only these two will do something like this. Look at what they do. By themselves, they will immediately split and become this gas and this H2O. This is a basic gas, fine enough. They are still basic, but they refuse to stay like this. They will split. He refused to stay like this. He will split. He will split. They are shy, or they don't like to be in this form. They don't like. Okay. So practically speaking, you don't get to see this much in real life, because the moment this happens or this exists, it is so shy that he will just split himself. And so this guy is, so to speak, no more lah. This guy is, so to speak, no more. And yet, for a guy which is no more and no more, it keeps popping up in the syllabus. It keeps doing that. Okay. Is it because CO2 is very popular and NH3 is popular? I don't know, maybe, but they do keep popping up. And the moment they pop up, they immediately split to, well, these two things and these two things. Only these two things do that in a very consistent way. The rest don't do that. You don't see HL splitting, you don't see this splitting and all those stuff. Like just that's just how O-level syllabus sees things like that. Okay. Any questions so far?
No.
One shy acid, one shy basic. The revision is basically done. Okay, the revision for acid and base is basically done. We go to salt. Now, give me an example of acid, Aiden.
Acid is HCl.
Example of base, Joshua. Joshua, you might be. Come on.
Zinc hydroxide. Finish.
For now, I'll tell you this is solid just to get used to it, and this is aqueous, right? Okay. So what will it become? We'll talk about it very soon. Another acid, Aiden.
Another acid, H2SO4.
Another base, Joshua. Something differently.
Hold on.
What is the list of base? Metal, metal oxide, metal hydroxide. Simple, right? And the digilo NH4OH though.
Na2O.
Okay. One more time. The basic list is even simpler. Metal, metal oxide, metal hydroxide, and one shy guy, NH4OH. Right? Another acid, Joshua.
H2CO3.
And another base, Aiden.
MgO.
MgO. Now, okay. So the first guy should be easy to predict the result, right? So they do react. So something kind of changes within them, and we get something else. Joshua, could you predict the result?
Water and salt. So it's H2O and is it zinc chloride?
And what's the chemical formula for zinc chloride?
Chloride is zinc is ZnCl, is it?
Cl is minus, right?
Minus 2 plus. Is it 2 plus? ZnCl2. Is it?
I forgot the 2 here. Okay, so roughly, you're correct, Joshua. Roughly speaking, people, is this reaction balanced or not?
No, there's
not balanced. So I'll start balancing. I'll just revise for you. So I'll deal with the zinc first, right? 1, 1, no, right? Because zinc is 1 and 1, right? In both sides, easy to see. And then I'll deal with the Cl, also easy to deal with if this is 1 and this is 2. Okay. Lastly, I'll just have to figure out what's the correct number here. Let me see the H. The H has 4. The O has 2. Well, clearly this must be 2. Do you guys follow the balancing? Do you agree or disagree?
Yeah, I
agree.
What do you think, Aiden?
I agree.
Okay. Then lastly, I'll add the status state symbol, not status, right? And this will be aqueous. If you don't know why is aqueous, why is solid, we'll talk about it like very, very soon, right? Okay. As you can see, Aiden, the initial mole chapters, the balancing is just everywhere, even in the previous chapter. This is considered your previous chapter, the chapter before the mole. It's gonna be there one. It's gonna be there.
Yeah.
Okay. Right. So this shouldn't be a surprise to you anymore. It should be almost natural. Now, let's predict the reaction for the second guy. Aiden, what will they become?
Na2SO4 plus H2O.
Right. And that's a very good start. Writing all the things are a very good start. Then this is liquid and this is aqueous. After a while, you get used to it. Now, balance it, people.
Already balanced.
Already balanced. So 1, 1, 1, 1 lah. Joshua, do you agree or disagree?
I agree.
So just to check, Na, very easy to settle, 1, 1, 1, 1. And then the other one very easy to settle is the SO4. So looks like this also 1, 1, 1. And yeah, I would agree with everybody lah. This last one is also 1. Okay, so 1, 1, 1, 1, very nice. Now, last one. What will happen? Both of you think. I'll give you half a minute to think. What will happen to the third thing?
It will become MgCO3 plus H2O.
Right. Okay. Let's see whether that is true or not, but I'm giving Joshua time to think.
MgCO3 H2O.
It will
And-
become Mg bracket CO3 to H2O.
Cannot be bracket 2 because Mg is 2 plus, CO3 is 2 minus. Yes?
Oh, yeah.
CO3 is nice.
Plus H2O.
Plus.
And it should be balanced.
Now, maybe to everybody's surprise, this will not be the case. It is not. Give you a simple explanation, because this is the shy guy. There's only one shy guy, right? What do the shy guy do? Somebody?
It's already water and carbon dioxide.
Immediately. He just do that. It's almost instant one, boop, like that. There are ways to make him not split, but you don't learn that in O level. We don't care, right? Okay. So right from the start, before anything could happen, he already split first. Okay, that's the first thing we have to notice. Okay, now H2O is neutral, so we'll say from the start there, we'll pretend that it doesn't react with MgO, right? We'll see later that that's not true at all. So but let's pretend that water does not react with MgO. Now CO2 by right is acidic. MgO is basic. So okay, now CO2 meets MgO. Is there another possible reaction? Maybe. What you think?
No, because CO2
Is
H2O is neutral already.
no, CO2 is not neutral. CO is neutral. Memorize it. So H2O neutral, CO neutral, and O neutral. CO2 is not neutral. It's very slightly acidic.
It will make hydrogen gas.
There's no hydrogen gas here. I'm not sure where you're getting that from.
Because CO2 is an acid plus the metal oxide.
Right. So, but again, if you just see this and this, there is no hydrogen between them, so they won't make hydrogen gas. They'll make something else, maybe, but they won't be making hydrogen gas. You're memorizing things, but when you look at the chemical formula, it totally doesn't make sense that a hydrogen will appear out of nowhere.
Oh, then you can just cancel the water because you still make MgCO3.
No, first of all, there is no MgCO3. There is none. You got it first. Because the CO3 is long gone. It has split to H2O and CO2. There is no more. There's no way that this is happening. No way. Because of the split. There is also no way that CO2 and MgO produce some sort of hydrogen gas. There is no H between them. Your memorization is now put to understanding, right? Okay. Lastly, they don't even have a chance to react because the CO2 gas immediately escapes. Bye-bye. They don't even meet. That is what is going to happen if you do it in lab. Can you accept such things, Joshua and Eden?
Yes.
At all then.
You okay?
So it won't react, right?
Because they don't have a chance to react. Why? Because CO2 escapes. Bye.
Okay.
Not interested to stay around you, MgO, he'll just fly away. Even though if you keep them long enough with various methods close by, they will, after a while, react lah. Don't know to what, but they will. Very slow. But even that has no chance of happening.
Okay.
So I'm not saying that, Aiden, you memorize, acid meets metal oxide becomes hydrogen gas. I'm not saying that that's wrong, but I'm saying that look at the details. Sometimes it doesn't happen, although most of the time it happens.
Yeah. So
That-
also
Yes.
you are saying that like all gas cannot react.
In some sense, sorry, let me finish it. In a O-level sense, that is almost true already. In O-level, most gases simply escape lah. What else can you do? You collect them, lo. That's all. You collect.
Oh,
Right. Not 100% true. Sometimes they force the gas through a solution. So you gotta force them through lah. You gotta force them through. Yeah, which is to say, for example, you bubble it through something, for example. And that can happen. So for example, something like this, for example, something like this. CO2, remember, slightly acidic, right? Slightly, right? CO2 gas, you bubble through NaOH. The reaction will look like this. Something will happen here. Although very slightly, something do happen. Okay? But very slightly, very slightly.
oh.
Yeah. But the bubbling thing is not something they are very focused upon in O-level, because in general, we just don't want to react gas because it's difficult to react gas. Again, why? Because they tend to escape. They tend to separate and escape. It's troublesome to react gas. So at the time you see gas and you immediately say, oh, the gas bubbles out. Yeah, the gas escape, that's it, nothing else happened. Something like that. We're being practical here, not just theoretical. Again, any questions so far?
No.
Right. Now, this should explain to you, Aiden and Joshua, later. If you want to prepare salt, it's a fancy word for, I just want to make certain salt. I want to make this salt, I want to make the salt. You never see a method which involves gas. Not that you cannot, but it's just super inefficient, but just asking for trouble to make it from gas. Okay, understand, Aiden? Not that you cannot, but it's just not practical, please. Something like that. Okay, so there's gas. Now, test you a bit more. More acid, please, Joshua. Oh, sorry. I'm so sorry. Let me do that. I'm going to put MgCO3 here, which we didn't create just now. Okay, this is supposed to be I just put them as. Okay, so give me one acid, Joshua.
HNO3.
Now, Aiden will know this. This is an acid, yes, nice, a very nice strong acid. This is currently not an acid and not a base. How do we know, Joshua?
It's not
in the list of the acid. It's not in the list of the base. Let me repeat the list of the base. Metal, metal hydroxide, metal oxide, and NH4OH. Does this look like metal, metal oxide, metal hydroxide, or NH4OH?
It doesn't look like any of them.
There is a metal.
But it doesn't, it's not an oxide.
This is a salt. This is a salt.
Mm.
Instead of this is a basic, this is a salt, the metal ion together with the non-metal ion. That's just that's what a salt is like, just metal ion with, right? So this is salt. Okay, now we're gonna ask Aiden. So is there any possible reaction here? You would have memorized this. I know that you memorized this. You mentioned this once to me. I know.
There's no reaction because acid doesn't go with salt.
And you are right, because acid don't react with salt, salt don't react with acid. That much is That much is true. That much is true. And yet, this chemical world is full of exceptions. This chemistry world is full of exceptions, right? Full of exceptions. Let me now explain what is going on in detail. And this is our first discussion for salt preparation. Okay, we are officially going more than just acid and base. Now, whatever else you understand about aqueous, there is one very important thing. Aqueous means they split. Solid means they don't split. That's what it means. Aqueous means they dissolve. How do they dissolve? By splitting into its respective ions. So in water, aqueous means in water, they dissolve. Again, dissolve means they split. This is of very important importance. Solid means they are in water, because all reaction that we do in lab is carried out in water, except for gas. Again, gas, right? But in water, they don't split. So they don't become Mg2 plus and CO3 2 minus easily. They don't easily split. That's what solid means in water, and that's what aqueous means in water. Any question so far?
No.
Right. Now, your teacher will say, hey, something happens here. Something happens here. What happens? Well, this will happen. It will become MgNO3 2 plus H2O. This will happen. And this will be plus, and this will be gas. So do you remember something like this, Aiden? Carbonates with acid will become salt, water, and carbon dioxide.
Yeah.
Okay. So could anybody explain why this is happening? It is true that if you do this in the lab, this will happen rather slowly, but it does happen. It does happen. That's true.
It happens because H2CO3 is a shy one, so it's split into H2 and CO3.
So you're saying that there is H2CO3 produced. That's what you see. You're right. You're right. This H2O plus CO2 is the result of the shy guy. But we don't see the shy guy originally, right? It's different from this one. This one, the shy guy is already there. So, it immediately splits. This shy guy must have come from, somewhere here. Not obvious. It must be produced somehow. Somehow. Do you see how it may be produced, Joshua and Aiden?
You mean the shy guy?
Yeah, because the shy guy is not explicitly here. If you are right, it must have been produced.
Because H mixes with CO3.
Yeah, more precisely H plus, yeah, not H, yeah? H plus meets CO3 2 minus. Is that what you mean?
Yeah.
Okay, so Joshua, are you okay? That's already half the explanation.
Yeah, okay.
So let me go for the full explanation. So one more time, I'm going in detail here already, right? So I did say to you that solid means they don't split. That is never fully true. Nothing is fully true in the chemistry one. What it means that a very, very tiny amount did split. The rest stays together. So let me give you a simple example. So 99.9% will opt to stay together as solid, and 0.1% will split and enter water. What's the difference with aqueous? In aqueous, 100% split, just like that, very fast. Okay, this split will later be very important. So how did the H2CO3 happen? This small amount guy will meet this guy there. The moment they meet, it becomes H2CO3, and the moment this happens, they immediately split to something else. leaving your Mg2 plus and NO3 minus to form this guy, something like that. Okay.
Oh,
Small amount, big amount, enough to make. Now, let me tell you something. The moment this is gone, some other guy will follow. Some other guy will follow very slowly. Other guy will, dissolve again and then react. Then dissolve again, then react. Then dissolve again, then react. Very slowly, this happens. You can see the bubble appearing, boop, 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 very slowly. Why is it very slow? Because this guy refuses to split very fast. He just split very slowly one. Very, very slowly. So the whole process is slow. But after a while, everything will be gone, and this is what will happen. Okay. This will be considered a reasonable way to prepare this salt loop, so to speak. It will be considered a reasonable way. This is our target salt. I want to make Mg nitrate. How do I do that? Oh, okay, sure. Start with this, mix them up. Yeah, blah. I get this one. Yay. Okay. Joshua, this is like the end part of acid and base chapter. They ask you to make salt instead of make acid and base. They almost never ask you to make acid and base. Don't know why, but they do want you to make salt. Right? And in the process, learn all the intricacies. I don't think they are interested in making salt. I think they're interested in giving you an idea how the chemical reaction works. I think that's the purpose of the chapter. All right, Ken, so far so good, Joshua? Okay, I'll give you another carbonate to emphasize the whole thing. Na2CO3. Different to MgCO3, which is solid, Na2CO3 is aqueous. There is a difference there. Then meet the same acid, HNO3. Then, right, so the question is, will something happen or not, Joshua and Eden?
I think something will still happen.
All right, what will that be, Eden?
NaNO3.
Na what, sorry?
NaNO3.
Right, nice, sure. And that will be aqueous, by the way, right? And then?
Plus H2O. Plus CO2.
Right. This will be correct. If you do this in lab, this will be true. Do you understand, Joshua?
It's okay, yeah, because it's a carbonate, right? And then it'll become salt, H2O, and carbon dioxide.
Right. So what will happen is this will become Na plus flying around, right? This will become CO3 minus 2 minus flying around, right? This will become H plus flying around, and then NO3 minus flying around, right? Because they're all equals. And then this will meet this guy, become the shy guy, and you're left with this guy and this guy. Simple. Okay.
Okay.
The difference between this guy and the guy below is the guy below will be slower. The guy above will be much faster. Okay. Infected by this one. No? This is ready to split. This is not very ready to split. Okay. So does this mean that, now let me ask you this, does this mean that acid can react with salt? Does this mean that?
No.
Why do you say no, Aiden? You look at the reaction. It really looks like acid is eating the salt or something like that, It looks like that one.
Acid is only eaten like 0.01% of the salt.
Which, let me correct, will continue to, after this is eaten, then another one will come out and then eaten, another one will come out, eaten, another one will come out until, it is finally gone. Yeah, it's just stopping at a very small amount. After a while, everything will be gone. So one more time, Joshua and Aiden, does this mean that acid can react with, salt? a neutral.
But the reaction is very slow, so it's like negligible.
Not negligible, again, even though it's slow, it will come to completion. Okay, and then when you look at this one, suddenly you have a fast one now. So this is a salt, and this is an acid, and this will happen very fast. Does this mean that?
How do you know if it's slow or fast?
I'm sorry?
How do you know if it's slow or fast?
Very simple. This is something very important that you need to know for salt preparation. Let's go to the next page for a while. This is easy to see, and you're supposed to see this in salt preparation. You're supposed to be able to see this, just like you're supposed to be able to see, oh, that's acid, oh, that's base. Okay, so something like this. Mix number 1 and number 2. Right? Number 1 and number 2 are both aqueous. Aqueous mixed with aqueous, right? Now, another one will be number 1 is a bulky solid, and number 2 is, this is just in water, and number 2 is an aqueous thing. Pour in. Number 3 is in water, still solid, but the number 1 solid is grounded into powder. This is one. And then number 2 is being put in. There are other combinations, but let's talk about these 3 first. Okay. Water is simple. All of them can react, okay? So number 1 and number 2 will react. It's just that number 1 is a aqueous base. Here, scenario number 1, number 1 is an aqueous base. Scenario number 2 is a solid base, and number 3 is a powdery base. What do you think will happen, Joshua?
I think like the first one will be the faster one, like to react, and the third one will be the second fastest, and the second one will be the last one.
First, and then medium. Now you'll be correct, but is there any explanation why to yourself? To yourself, you need to understand this more than the whether the examiner is going to ask you or not. This you need to understand. What's the explanation here?
The exposed surface area.
All right, of number 1 is the slowest. Let me draw for you the exposed surface area, which is here, right? Yeah. So you only have this surface area to work with, is very slow. Furthermore, the surface area will reduce because S1 reduces. So this is not helping. This is not helping a lot. What is the surface area for scenario number 3? It's well, it's hard to draw, but I mean you can see that it is really a lot because they are all in powder forms, something like that. Much more than scenario number 2. Now, if scenario number 1 is the fastest, then its surface area should be even bigger than scenario number 3. Is that the case, Joshua and Aiden? Why is this the case, or is there something else going on here? What's going on here?
I mean, for the fastest one.
Yeah, like why is number 1 the fastest? Number 2 and number 3, you know the answer, the surface area exposed, right?
Because they are like there's like the surface area is even more here.
Why is it even more in scenario number 1?
Because they are all like liquid particles, like liquid particles are, this one is solid particles. Solid particles are larger than liquid particles. Liquid molecules are like smaller.
You're going in the very right direction. Joshua, do you have any additional thing to say?
No, not really.
Right. So let me try to complete Aiden's explanation by making it this way. What you call liquid particle is actually the dissolved thing. So NaOH is aqueous, means NaOH does dissolve in water. What does dissolve mean? I do tell you that dissolve means it's become Na plus and OH minus. This, how small is an Na plus and OH minus lah, compared to this powdery particle? That's what Aidan is trying to say. So how small is this compared to that?
Number 3 is bigger compared to that.
Number 3 is bigger. It's a small powder. It is still bigger than this. How do we know? Because this is quote unquote a powder, so to speak. Like, yeah, it's not really powder, just quote unquote powder, the size of a molecule. Na plus is an ion, I know, but just consider it the size of a molecule. My point is, can you go even smaller than this? Can you go smaller than Na plus?
No.
So to be aqueous is to be the extreme smallest powder, so to speak. Therefore, the highest surface area possible. There is no other way to make it faster. Therefore, the fastest reaction. It is extremely, extremely, extremely fast. Okay.
Okay.
Why is therefore aqueous important? Because aqueous will affect the rate of, reaction by a lot, and that kind of determines quite a lot of things. Going back to the previous page, this is aqueous and this is solid. This is scenario number 1 and this is scenario number 2. This is the slowest and this is the fastest. Something like that. Can you?
Yeah.
What does this have to do with salt preparation? You'll see later. You'll see later. Any questions, Joshua and Aidan?
No.
Okay. So again, let's look at salt preparation. We were talking about acid and base here. Oh, a very nice acid, a very nice base. Hey, we have a solid salt preparation, right? I mean, it's not very different from acid and base. Salt preparation still start from mixing one acid and mixing one base. Hey, we got this salt. Hey, look at this, another salt. Hey, I'm preparing this salt. I'm preparing this salt using, various forms of acid and base. Also, I'm preparing this salt by using, an acid and a carbonate, a carbonate. Oh, I can do that. There are various ways to prepare it. So now I'm going to tell you what works and what does not work. Okay, what works and what does not work in salt preparation, so that you know how to choose. Now, at this point, if things get hazy, you tell me, we stop, we repeat. If this is too hazy, I'm not interested to continue. I'm not trying to be fast here. I'm not trying to cover things and finish the chapter. I'm really trying to give you understanding which may not be given in the class. That I hope will help you. So if things are very hazy, you better ask, or you at least ask me to stop.
Okay.
Remember, we're not trying to rush things and finish things. This is not what we're doing. So this is the target salt. Okay, this is water, so that's fine. Now, this is scenario. Okay, I'm gonna give you the scenario. Scenario number 1, scenario number 2, which is like that, a lump, and then scenario number 3, which is a powder. 1, scenario 2, scenario 3. So this scenario is scenario number 1, number 2, or number 3, or maybe there's another scenario. Which one?
This one is scenario number 2.
Number 2.
Number 1.
1. Okay. So no, 1 is aqueous with aqueous. The best, the fastest way. This is not aqueous and aqueous, so it's automatically not scenario number 1. Would that be okay?
Because it's solid here, then it's number 2.
Correct. So it's number 2. However, just to be clear, Joshua and Aidan, practically we avoid scenario number 2 as much as we can. Why? Why do we avoid 2 as much as we can? We go for 3. Why?
Because 2 is slow.
Yeah. As much as possible, we avoid 2. right? There are reasons, there are certain situations where you can go with 2, but in general, we do not want to at all. We just avoid 2. Why am I mentioning 2? Because it is how you will imagine it if you're not in the lab. You will imagine a bulk, and then you're gonna mix this. That is gonna take so long, man. Like really so long. So we avoid that. Okay. In lab, we always say get a powder form of the zinc hydroxide. You don't have the powder form, let's not do this experiment. It's gonna take so long, right? So scenario number 3 is here, just to remind us. Now we have a problem. Let me describe to you the problem and let me ask you the solution if you can offer one. The problem is very simple. After I react this is gone. And this, you know, there's remains some. So this is gone and we have the salt. We have a problem. Joshua and Aiden, do you see the problem? No, no problem from Aiden. How about you, Joshua? Do you see any problem?
The remains, the excess, I don't know.
The problem? This is the
this salt is mixed with this, so there's like excess.
Okay, you're saying that they will be mixed, which I mean, we agree with that. They will be mixed, right? They will be mixed. Now, let me confirm this. Do they react? Will this HCl acid react with the salt? Will it happen?
No.
It won't, but it will be
Acid
impure.
don't react with salt, right? In general, just no. Acid don't react with salt. So they won't react, but they will be mixed. Are you saying that that's a problem or not? Sorry, Joshua, Aiden, what are you saying?
Because being mixed will make it impure.
You are absolutely right. Salt preparation implies that it needs to be pure. Implies they never say that, but that's what they want. You don't want salt and then mix with acid. You also don't want that. You know, people sell you salt. You know, table salt tastes very nice. Mixed with acid 1%. You don't want that. Not nice for cooking. Not nice for your, you know, not nice for your stomach. Not nice for your tongue. I want it to be pure. How do we solve this problem then?
Like my school tells me, like filter.
Filter. Now let's be very clear. Aqueous is the smallest powder possible, so to speak, right? Remember, that's what it means, right? Aqueous, to be split into the smallest thing possible. This is the smallest thing, and this is the smallest thing. Is there any way for you to filter that?
You can't filter it.
You can't. Just to be very clear, you can't. You have a big problem if you want to filter it. You can't. You cannot filter this from this. No way, man. Just no way. That's not going to happen. Because the advantage is they're the smallest, and that is also their disadvantage. Look, they are also going to be a problem in some other ways.
Oh, then the other one is crystallization.
If you crystallize this mixture, remember this is mixed, this will crystallize together with him, and therefore you have a crystallized salt, which is not pure, which nobody wants in practice. Nobody wants that.
Then you do, is it titration?
Titration, which is a very, titration means something like this. You're going to mix an aqueous with another aqueous. That's the prerequisite of titration. You cannot titrate a solid with an aqueous, if that makes some sense.
But this one is aqueous, this one also aqueous.
Which one? Yeah, but titration means you're trying to react with them. You are not trying to react them, and they cannot react also. You are trying to make sure they are not being mixed currently. You're trying to separate them, if possible. Titration is not a method for separation. Clear? Titration is.
Can you try distillation?
What was that?
Distillation.
Distillation means something like this. We're reviewing all your secondary stuff. I like your thinking, everybody. Distillation means whatever is dissolved, right? Whatever is dissolved, which are liquid or aqueous. You can say that, right? The liquid portion will evaporate in distillation. Now, let me ask you, if I distill HCl aqueous mixed with ZnCl2 aqueous, who will evaporate? Who will evaporate? Who will evaporate if you try to heat this up lah, heat these two things up?
Hydrogen.
No. There's no hydrogen gas here. Let's just be very clear.
Chlorine.
In some sense, but no. Let's be very clear. The H2O will evaporate. The water lah, aqueous ma. You'll be left with ZnCl2 crystals to get mixed with HCl, which can be crystals. You just never see them. This is your crystallization, no, Aiden? Crystallizing is heating them. Joshua, distillation is also heating them. Basically, that's what distillation means. Heating.
So it still works, right?
So as in a sense that this doesn't work, it doesn't work. The ZnCl2 will not evaporate. The HCl2 will not evaporate. It'll stay behind. Your H2O will evaporate. It doesn't help with the impurity problem. Okay, but I like your ideas because you're bringing everything from term 1 and term 2 lah. But no solution yet. Any other ideas?
You put distilled water.
You're diluting them. You're adding up water to them. But how does that help you in separating them when they're already aqueous, when they're already dissolved? Now, any idea to try at this point? Any other ideas to try?
Well, isn't that the question is impossible?
No, very possible and a very easy solution some more. That's why I want you to know it's a very easy solution. A solution that makes a lot of sense some more.
Then you can react the acid with something else, right?
Okay. Let's say the impurity is, currently we have this. Currently I have ZnCl2. Okay, I guess you can do that. I guess we can mix with HCl. They don't react. So what do?
You put like a base inside and react with the HCl, and then HCl is gone.
Propose a base to react.
Like MgO.
Okay, so now MgO lah. Right? So plus MgO. So let's be clear. This will be gone, right? This will be gone.
Yeah.
This will remain, correct or not? You cannot make them both gone at the exact point one. You cannot. One will be gone and one will remain. This is a very practical way of reacting. Am I making any sense?
But MgO is solid, right?
Yeah, solid. You're right. MgO is solid.
Solid.
Correct.
Then you can filter this because it's solid.
Very good. Very good. You're getting to the point here. So now you change the problem, right? The problem originally is aqueous mixed with aqueous, but now you change our problem into solid mixed with aqueous. I can filter the solid one. You are absolutely correct. That is a solution. Does that make sense, Joshua? That is.
Although it makes sense, I haven't heard this like in my textbook or like.
No, I'll show you the simpler way, but you're getting at the right idea. You're getting the right idea, Eden. Don't worry. Joshua, does it make sense? Joshua, you're muted maybe.
Hold on. Filter the solid.
Aqueous with aqueous cannot filter, cannot distill, cannot separate, correct? Cannot anything like, cannot.
Yeah.
Okay, Aiden proposed to, swap our problem. Let's swap our problem with now aqueous and solid instead. By reacting the HCl away, the impurity away, and the other impurity is now MgO lah. But this is a different problem. This is now solid mixed with aqueous. You can filter the solid out quite easily.
Okay.
Yeah. Won't you get like MgCl if you do this?
You do. Oh my goodness. You do, isn't it? MgCl, which is aqueous. This is very unfortunate. This is very unfortunate. You now have this problem. Very unfortunate. Very unfortunate. Now, Aiden, you're thinking things through lah. You're thinking things through. You're right. Wait a minute. Now I have this impurity also. Hey, I didn't solve the problem. You're right. You're thinking things through. Okay. Now, let me show you the proposed solution in your textbook. The proposed solution looks like this. Just swap this law. Swap this. What do I mean by that? What do I mean by that? Make this gone and make this remain.
How do you do that?
By adding more of the solid guy. More until he is gone. And therefore, he remains.
Oh, so it is like the adding excess method.
Yes, that's why the word excess is what they ask you to memorize. They do ask you to memorize that, but the point is this. The aqueous problem is gone. You only have solid with aqueous. Hey, filter separate, done, no more problem.
Zinc hydroxide then.
Yeah, excess zinc hydroxide. Excess zinc hydroxide with HCl.
Okay. So you make the, okay, all right.
That is the right start. So as you can see, Joshua and Aiden, salt preparation is just acid and base, but with appropriate practicality. Let's be practical. I want a pure salt, so I want to choose the proper excess. The solid low will be my proper excess. That's what it means. They, however, will probably present this as a memorization or a step. Do what you want, but get it right, whether by understanding or by memorization.
Oh,
Do you understand, Aiden?
yes.
Yeah. So excess solid is very important here. You cannot let the aqueous be excess. Yeah, you cannot. Let's give you another example, and hopefully that's not too much. Let's speak from the target. Now, one of the things that salt preparation will do is not going to give you the product and not going to give you the starting. They will ask you for the starting one. They will give you the product instead. That means the target. Now, let's set a target salt, which is now solid. Previously, our target salt is aqueous. I'm gonna put that here first. Our previous one, the target salt is aqueous, right?
Yeah.
Now our target salt is solid. Let's see whether there's a difference or not. Okay. So Joshua, give us a a target salt which is solid. If you sorry, you don't know my solubility. Sorry, you don't know it's not insoluble. Sorry, I should be asking Aiden. Aiden, give us a target salt which is solid.
MgO.
MgO is solid. MgO is not a salt. How do we know?
Oh.
Base is metal, metal oxide, metal hydroxide, and NH4OH. So that's a base inside. So target salt.
Copper sulfate.
Sorry, what sulfate?
Copper sulfate.
Copper sulfate. Wonderful. Copper sulfate is not a solid. That is actually soluble.
Oh, then.
The exceptions for sulfates, if you remember your solubility table.
Exceptions for salt. Oh, calcium sulfate.
Yeah, nice. Thank you very much. Right. So, Joshua, what were we talking about? They kind of give Aiden the memorization table also. They memorize who is soluble and who is insoluble. Never mind for now. Okay, never mind for now. Let's accept the fact that calcium sulfate is solid, so insoluble. That's our target salt. Joshua, you're gonna make a proposal. What with what to create this? Aiden, you're gonna make another proposal. What with what to create this? Please propose. Okay. All right. So Aiden has a proposal. Okay, done. So far, so good.
Hold on.
Okay, Aiden, I'm going to help you write lah, yeah. So you have made your proposal. Let's just confirm what the result is lah. So by right, there should be a CaSO4 as a result, right? By right lah, right?
Yeah.
And what are the other stuff?
It is H2O and
Right.
CO2.
Yeah, H2O plus CO2. Okay, which is this is liquid and this is gas. Okay, that is a good thing, right? So Joshua, are you going to propose the same thing? Please don't propose the same thing. You don't get to propose the same thing. Propose something slightly different is fine. Okay, Joshua, to make a salt, must it be acid and calcium carbonate? Oh, your proposal is calcium metal, isn't it? I'm so sorry.
Yeah, I'm trying to.
I didn't get that. I didn't get that. Sure thing.
Okay, yeah.
Okay, so this will be extremely explosive, but it will happen. For the sake of theory, we'll assume that this is practical because it does happen now. It happens too fast, such that it is explosive, right? It is explosive. You haven't learned why this is explosive, whether this is even explosive, but we're gonna pretend that nothing dangerous happened. We're gonna pretend that this is fine and this is practical. So let's do that. Okay, let's do it. This is aqueous and this is solid. Okay, now let's talk about Aiden 1 first. Aiden 1 first because Aiden proposed this first, right? So in general, do you agree that the reaction happens, Joshua?
Yeah.
Because the reaction might be wrong, you know.
Mm,
It's up to us to decide whether the reaction is correct or not. Then I'll agree with you, right? This is acid, this is a salt. Hey, how come acid with salt react? Because you know when this one split blah blah blah, it'll form H2CO3, which will immediately split. However, this will be a little bit slow, but that is fine. There's nothing wrong with a little bit slow. Now, from the practical point of view, which is the salt preparation point of view, from practicality point of view, is there a impurity problem or not?
There is, right, but this time now you add excess of this.
Who will you be accessing? All right, so you decide that this will be excess. So this will be gone, right? I mean, cannot be both excess, right? One will be gone, will be excess, right? This is our target. Therefore, you propose that this solves the impurity problem. How does that work?
Because there will be no more liquid, so everything is solid.
You're not making sense. So this is gone. I agree. This remains, but there's this one. So now they are mixed. They are still impure in some sense. So how do you plan to solve that problem? They're still mixed, you know. They're still mixed. Filter, correct? That's simple. Filter this guy out. That's how you separate this from that. Okay, then filter, wash with ionized water, blah, blah, blah. Those will be the steps. The moment you filter, you're already at the right track. Joshua, are you clear? That's how we deal with it.
Which, if it's like impure with what though?
I'm sorry, you're saying?
How do you know if the salt is impure with like? How do you know which one's the excess and which one's the?
Yeah. You only have two options. First thing first, right? You only have two options. Either make this excess or make this excess. You have to choose the scenario which is better. If you make this excess, this is gone. So now this and this, you know, coexist together. Is that good or not? Good. You can just filter.
Okay. Oh, okay. I see what you mean.
Yes. Now,
okay.
Is that good or bad that this solid powdery thingy coexists with this solid powdery thingy? Is that a good idea or not?
No, because they're both solid and it'll be harder to separate.
Almost impossible to separate one powder from another powder. Not gonna happen. Okay. How do you remedy that? Just add more H2SO4. Then suddenly you don't have that problem. Correct or not?
Yeah. Okay.
Yeah, that's way to solve the practical problem. So far, so good. Okay, understand. So far, so good. Now, let's look at reaction number 1. So again, will this reaction happen? Just to be clear, will it happen or not, people?
Yes, it would.
Yes, what? So there's no problem with the reaction theoretically per se. Let's go to the practicality of things. So practicality, do we have an impurity problem?
No, right? Because this one is just going to evaporate.
Correct. As
Mm.
same with yours. This is not evaporate. They will just escape. We'll just call it escape. Yours also, this will escape, that's why we like CO2. Bye-bye. No need to bother me anymore. H2O is not a problem at all. So you're right. This is no problem. This is no problem. This is no problem. You are correct. The problem is here. The problem is in front. Joshua, will there be a problem or not in front? Will there be a problem?
Hmm. Hmm. Uh.
Look, in a reaction, practically, both are not gone. That's what you must understand. One will remain one. That's the practicality of the lab setting. You cannot make both gone. It's extremely difficult to make both gone. It has to be, very accurate. Okay. So you get to decide whether this is gone or this is gone. What's your preference?
For the calcium to be gone.
Right. And therefore, just add more H2SO4, right? That's just how you do it.
Mm-hmm.
Actually, a very easy thing to do. It's not gone. Add more loop. Boom, it's gone. This is excess, and this is the target. So, are you happy with?
Oh, okay.
Are you happy with this?
Okay, I get it. Okay.
It's simple to separate the aqueous guy from the. Oops. It's as simple to separate the aqueous guy from the solid target. It's simple.
Okay.
There are 1 or 2 more concerns, but I have basically covered salt preparation for you guys. Look, I have, yeah. That's the main concern of salt preparation. Are you going to get a pure substance or not? Can you do it? If you cannot, it's not practical. That's what salt preparation chapter means, right? With that, you have to memorize the solubility and insolubility. Now, Aiden, now you know why they ask you to memorize the solubility insolubility table. As in, now do you know why?
Yeah.
Because the solubility and insolubility matters for purification. So Joshua, you don't have to memorize right now, but me and Aiden kind of getting it in our memory, like, okay, this guy is solid, man. This guy is aqueous. It matters. Today, I'm just saying to you, Joshua, those things matter practically. Okay? Will that be okay, Joshua?
Yeah.
Now, let me explain the last most annoying method of making salt. Let me repeat this. Let me repeat this. Let me make this clarify. This is so easy to do. Why? Prepare this, pour this. Hey, not gone. Pour more. Done low, then filter already. It's not difficult to do in lab. You like this. Same thing with this one. I prepare this powder, I prepare this, I go and pour this here slowly and stir. The powder is not gone. Can you differentiate this powder from this powder? Actually, I cannot. I don't know whether the remaining one is the original carbonate or the CSO4 that I'm targeting. To be safe, I add more, I just add more acid load, add more, until I observe no more CO2. Then I'm sure there is no more CaCO3 because I can't really differentiate between them visually. Can't really do that. They're both white. Okay, but I can notice whether the CO2 stops being produced or not. When the CO2 stops being produced, I am certain this is gone and this is in excess. How many minutes does that take, you think?
Not a lot.
No. Probably less than 2 or 3 minutes. You're just pouring stuff and stirring stuff, and no more bubbles, stir a bit more, no more bubbles, stir a bit more. Okay, no more. Yeah. Really, no, it's less than 3 minutes. Believe me, because you haven't done a lot of practicals. Believe me, though, this is one of the easiest thing to do. Okay, so again, why am I saying this? Because practicality matters. Now comes titration, which is a very annoying thing to do in lab. Titration. You guys are done titration in lab? No, yeah, Aiden have not, yeah, titration in lab. No, yeah.
I have tried it already. I have tried titration.
You tried titration. Good. How about you, Joshua?
Yeah, I did titration.
All right. Let me confirm that to do titration, it is not a very short process.
Yeah.
How do you remember how long does it take for you to titrate properly?
Maybe 10 minutes.
10 minutes?
Around 20 for me. I don't know, 20.
I wouldn't be surprised, 10, 20. It's not 3 lah. It's not 3. First of all, you don't get to pour everything into boom, right? You don't get, right? You have to pour it into the burette thingy, right?
Mm.
Then you have to open the, thing so that the drop, toop, toop, toop. Before the drop hits, you have to put in all sorts of indicators and all those stuff so that you can see the end of whatever they call it, the end of titration, right? Do you know what happens if you if you titrate over that point? Do you know what happened?
It turns pink.
I'm sorry?
The middle orange turns pink.
Correct. And if you accidentally add another drop beyond that when it turns, do you know what will happen?
Then it will turn more pink.
Yeah, the whole problem is if this is making salt, if you are using titration to make salt, you just overshoot and you have to repeat the whole thing again. It's not fun. It's not fun to make this to use this method to make salt. Let me explain what that means. So again, one more time, I'm telling you, titration is not a very practical way to do things if you want to make salt. It's really not. It's really not. Because it takes longer and there's human error involved. Whereas excess and gone method, I mean, what's so difficult about that? Just make sure one is excess. Just keep adding until you're sure. Okay. So now let's talk about titration and let's see whether there are merits, because I've been discussing the disadvantage. Okay, I've been discussing the disadvantage of titration. So titration works like this. You have done it in the lab. It will be one aqueous guy with another aqueous guy. Can I titrate one aqueous, one solid? Is that possible?
Titration is both aqueous.
All right. So let's stick to that. You are correct. There is nobody will titrate solid with aqueous. There is no point anyway. So it'll be aqueous and aqueous. To produce what? To produce another aqueous. To produce another aqueous. Here lies the problem. If this is gone, this is excess. Do you see the problem?
Yeah, then it will be pure.
Then I reverse, right? Generally, they just reverse now. Okay, now this is excess.
No.
This is gone.
Everything is equivalent, so it doesn't matter which one is excess.
So both is a problem, no? You see what I mean, right? Both is a problem. Like, why do this, man? Like, why do this? Why do we do this? I don't know.
Like the exact number.
Yeah, precisely. That's what titration means. You're going very slow because you want to be exact. What does it mean to be exact? You want both to be gone. That's what titration means. Why do you titrate? Because you need to be exact. Why? Because you want both to be gone, which is a very difficult thing to do. But sometimes they ask you to do this, whether theoretically or in the lab. It's not fun. So Joshua and Aiden, let me give you an example, right? I want NaOH, a very simple base, and I want HCl in order to make, obviously, NaCl and plus H. This is a very simple reaction to understand. However, it is a very annoying reaction to do practically because both have to be gone. Do you understand?
Yeah.
Now, let's go for the next page, and this will be the last reaction. I am going to have H2SO4. And then I'm going to have, what should I have here? No. They're very rare examples for this. Okay. This is slightly soluble. So this is like, yeah, I guess I can do that. I guess I can call this aqueous, right? It's not fully aqueous right now. Then this is H2SO4. Aiden, you should know that CaSO4 is soluble or insoluble.
EaSO4 is insoluble.
Good. Observe these people. I start with unaqueous and unaqueous, and my target is solid. That is different from the previous example, slightly different, right? Where the titration one. Yeah, I'm comparing it for you. The difference is because even though this is aqueous and aqueous, but this is one is solid and one is aqueous. So this one is titration. My question is, this new reaction, we titrate or not?
You don't titrate this. This one is precipitation.
Correct. This is precipitation. Why do not need to titrate? Why do not need to be exact?
I mean, titration will also work, but then it's like complicated, right?
I know. So my question is, why do we not need titration?
Because this one is insoluble.
Good. So whether this is excess or whether this is excess, it doesn't matter because this is solid, easy to separate.
Yeah.
Okay. You don't need both to be gone. The result is solid. So it's easy. Joshua, do you understand?
Sort of.
Okay. To emphasize the point, and then we close, yeah? If my result is aqueous, these two are aqueous, I'm in big trouble. Both have to be gone. Then I have to titrate. If my result is solid in this case, and I start with two aqueous, I'm very happy. Whether this is excess or this is excess, it doesn't matter. Aqueous with solid, easy to filter. Aqueous with solid, easy to filter. I'm happy. No need to titrate. Very fast.
Oh.
Understand, Aiden? Understand, Joshua?
So this is the easiest of the three, right?
I mean, anything which doesn't involve titration is easy one. As a bonus, starting with aqueous and aqueous makes it extremely fast. This is situation number one, remember? That's a bonus though. It's a bonus that it happens very fast. So would you call it the easiest? I mean, I guess you're right. That is the easiest compared to the other one, which you have to mix solid with aqueous. There are more practical stuff to consider. The powdery, the stirring, the making sure of stuff. This one, just boom and happen dah. No need to stir, no need to nothing one. Fine. This is the easiest practically. This is the hardest practically. You are right.
Yeah.
And Aiden, if you go and memorize all this, useless to you. Just add to your burden. Don't. Either you understand it or just memorize what your teacher asks you. I'm not asking you to further memorize this. I am imploring you, try to understand it. Your life will probably be easier. Okay. So Aiden, I have revised salt preparation with you. That is all I want to say. The rest is just to see what the question does. We'll be doing question later. Okay, you should have more confidence lah in all this. Okay,
Yeah.
let's see whether that's true or not later. Okay.
Okay.
For you, Joshua, I did review to you the most important essentials of acid, base, and salt preparation, like that. Yeah. If you are interested, you can look at certain exam questions and see whether you understand or not. Usually, you will feel happier if you understand. If you don't understand, don't feel that one. Now, this is the future topic, who cares, right? Okay. But if there is other past problem, I would rather talk to you about that. This is just the future. I finish introducing to you this topic. Okay. Okay, Joshua.
Okay.
Right. So for you, it's 1.5 hours, right? So I will see you this week. I'll just see you in the normal timing.
Yeah, normal timing.
It's Wednesday, right? Which
Yeah.
is
Tomorrow.
okay.
Yeah.
Okay. So Aiden, now this is just a question for you. Yesterday, 1.5 hours, you seem very fresh. I'm very happy. Today is definitely more intense. It's 1.5 hours. Then you say you may want to try 2 hours. Now, this is just, I was going to try with you 2 hours next week. But right now, do you feel that maybe you can try 2 hours and see what happens?
I think we can do the 2 hour next week.
Yeah, then next week then. Because today I'm quite happy. I'm quite happy with what we did. So at night later, we will be jumping into exam level questions. Can you'll be doing them, we will discuss. It is more like a normal tuition, like because you're consulting the question, you'll be doing them and then I'll be asking them what is your problem. Okay. Yeah, so we'll try that at night. Okay, good job, Joshua and Aiden. I'll see you when I see you.
Okay, bye-bye.